Okay, so in this video I'll be showing you how to set up a HEEDS project where HEEDS changes the height of the winglets, as you can see here. Then it will perform a fluid simulation and then use the solutions from that fluid simulation to perform a stress analysis. So to do this, I have two models set up. I have the winglet parametric model basis, so that's the original winglet model. And then I also have another version, the extrude version, where as you can see there's a extrusion added at the wing root, and this will be used to constrain the model. Because if you would use this this model, because this is a symmetry plane, you're not allowed to fix that, because then the symmetry plane cannot deform anymore and you will get stress simulation at the trailing edge. So that's why we use an extrusion, so that we can fix this plane of the extrusion and still allow the symmetry plane to move within the plane and deform. So I also named a few edges, some faces. So again, the winglet tip is named. Also in this one, the plane that we are going to fix is called the fixed plane. And then if we hide the extrusion, this plane is called the wing root. This face has to be named as well, because we're going to constrain it later in STAR CCM+. Okay, so first we have to set up the geometry. So I'm going to import the extrude version, the step file. And as you can see, this is a different type. So this is the icon that signals that this is an assembly. And then within that assembly, we can find two parts, which is body 1 and body 2. I'm going to change this geometry seam that it only shows this this parametric model, so that we have a clearer image of what we're working on. So I'm just gonna take this assembly and then make sure the representation is set to geometry, otherwise this won't show. Alright, so we have body 1 and body 2. Now, one thing I'm going to do is create tags. These will be very useful later on when we're going to use filters to select, for example, body 1 and body 2. So I'm going to create 4 tags. So body 1, body 2, then wing model and wing foil surface. And now we're going to tag these geometries. So here in the properties panel, you can add tags. So this is the wing model. This is body 1. This is body 2. So body 1, body 2 is our wing model, and then the surfaces, I'm going to tag them with the foil surface tag. Okay, so that's pretty much the geometry setup. Okay, so now we have to set up the continua and the regions. So I'm going to create a new physics continuum, and this will be the solid physics. So these are pretty much the properties of your material. So we're going to select the model. It's still three-dimensional. It's going to be a steady simulation, and then we're going to use the solid stress model. So we're going to add a new material law. Select the models. elasticity, and then isotropic. These are, of course, specific for your application. Then the material properties. So right here, we're going to select this material law. So here under type, we select material law 1, which is this one. And here we can change all the different properties of your material, like the density, Poisson ratio, and the Young's modulus. I'm just going to leave these as it is. These are the standard values for aluminium, I think. Okay, so that's the physics setup. Now I'm going to create the region. So again, same as before, assign parts to region. Create one region for all parts. You could also create one region for each body, but I'm just going to create one region. Now create a boundary for each part surface, very important. And then this one is also very important. We have to change this to create contact mode interfaces. This is because we're working with the solid stress model, which isn't compatible with the boundary mode interfaces. So you apply this, then this region is made. I'm going to rename this to solid region. Change the physics continuum to solid physics. Then we have our different boundaries, and we can see that the interface between body 1 and body 2 is automatically created, and that's what we want. You can also check it over here. Okay, so now an important step here is to change the parts for the region. Change the selection type to a filter. So this is where the tags come in. So we can just type tag here, contains, tag contains, and then we want the full assembly to be assigned to this region. So we just take the winglet, the wing model. So now when we delete this and then import this again and tag the parts correctly, this region should be automatically set up. And the reason for this I'll explain later, because that will have to do something with the heats. So for the mesh, a similar process applies when we made the fluid simulation. So we're going to make an automated mesh. Now select this one, a surface remesher, and then the tetrahedral mesher. Obviously not a prism layer mesher, those are the only two we need. I'm going to rename these to solid mesh, and then the other one fluid mesh, so everything stays clear. Now again, we want to change these input parts into a filter, so the tag contains, and here we can actually select the tag from the assembly. Now for default controls, I'm just going to use some values that I use in my other simulations. So base size, I think 0.08 or 0.8. I'll have to check. 0.5, oh, 0.8 is good. Then the target surface size will be 5%. This one 0.2. The growth rate, I'm going to put the slow again. Volume growth rates to 1.1. And for this, I'm not going to define any custom variables, custom controls. You could refine near the trailing edge and near the winglet tip, but for this demonstration, I'm not going to do that because it will increase the amount of time it takes to simulate all of this. So now we're going to set up the data mappers. And what these things do is they will map the solution data from the fluid simulation onto our solid mesh, so that, let's say, the pressure distribution over the wing can be used for the stress simulation. Now the data mappers are located under Tools, and then here Data Mappers. We're going to create a surface data mapper. The source surface will be from our fluid region, the wing surface, of course. Now for scalar field function, we're going to map the pressure distribution, and also, oh, that's a bit too much. And then also the shear stress distribution. If I can find it, wall shear stress. If you would use a volume data mapper, the wall shear stress will not show up, so it's pretty important that you use the surface data mapper. All right. So now the target surface will be the surface from our solid region, which is the foil surface and the winglet tip. So that is pretty much the data mapper setup. We have to use, we're going to have to give these some names. So the wall shear stress, shear load foil, and the absolute pressure I'm going to name pressure load foil. Okay, so now we're going to have to constrain our model, because now it will just fly off into space if we don't do anything. To do this, we're going to create surface segments. So first I'm going to fix this plane over here. So the type is a constraint. Surface will be the fixed plane. And that's pretty much that. Now I'm going to create another constraint, and that will constrain the symmetry plane. You can change this, the type of this boundary to symmetry plane, and in theory that should constrain this plane to the plane itself, so that the points within this plane can only move within the plane itself, and not in the normal direction to the plane. But in my experience, I found that this wasn't enough. These points will still deform outside of the plane, so that's something we do not want. So I'm going to constrain this even further. So the wing root, constrain, and the type is not fixed but normal displacement. So what this does, you put the normal displacement to 0, which means that the symmetry plane, the points within the symmetry plane cannot move in the normal direction. Okay, so our foil is constrained now, so we have to add the loads, so the pressure load and the shear load. Pressure load, shear load. So the load is correct. It will only be applied to the foil surface and the winglet tip. The method is a pressure, and the method is a field function, because what the data mappers do, they create a field function of the data from the fluid region, so that we can use that field function for the solid stress simulation. and the names that we gave earlier will show up for the field functions. So we have the pressure load. Oh yes, of course, I haven't executed the data mappers yet. So we map this data, so that's finished. Now the field functions should be created. So we should have pressure load foil. Apparently not. Okay, I made a typo here apparently. Pressure load. Okay. And then even an easier way to make the shear load is just to copy this by dragging this to segments. And then you only have to change the field function to shear load. Okay, so now our model is fully constrained and the loads are applied. I think I actually made some solution, okay. So we can actually visualize those loads. So if you make a scalar scene and call this pressure load, we don't actually need this one. And we can actually plot the field function of the pressure load. And this should show up. Of course, we have to get this part. We can actually use the tags, which is pretty useful. And they're just to foil surface, and then all the surfaces from the wing will be selected automatically. And there we go. We can see the pressure load, and we can do the same thing for the shear load. So just change the displayer, shear load foil, and there we have the shear load. So now we're going to add some post-processing things. So first we're going to make a maximum report. Field function will be von Mises. So that way it will calculate the maximum stress that occurs in the model. So the part will be again with the filter, tag body 2, because we only want to calculate the maximum stress from the wing itself and not from the extrusion. Then we can create a monitor and plot from that. Now another thing you can do is to visualize the displacement. To do that, we're going to make a new derived part, which is a was it a vortex? A vector warp, that was it. So the part is going to be, again, going to use the tags. The tag and then body 2. Or apparently I can only, I think I can only select surfaces. Okay, so the surfaces, the field function will be displacement. Scale factor, I'm going to up this a little bit because the displacement will be pretty small, so that way it will be actually visual. You can actually see the displacement. I'm going to create another scalar scene which will visualize the displacement. So the outline, I'm going to change this to a surface displayer, which will show the undeformed parts. I can just use this one. And then for the scalar parts, which will be the vector warp, and then scalar field function will be displacement again. Okay. This, I'm going to put this to geometry. There we go. So now we should be able to solve this, this simulation. So right now, how this is currently set up, both physics are currently active. So if we would solve right now, both the fluid region will be solved and both the solid region will be solved. Now, of course, this can be quite intense for your PC. So an easy way to switch between the solid physics and the fluid physics, you could do this manually by deactivating the physics and then freeze the solvers. But of course, there is a better way. So to do this, we're going to go to timescales. We're going to add a new timescale. I'm going to add 2 timescales. One will be the fluid physics and one will be the solid physics. Fluid timescale. Now this has a few advantages. If you go here, the active timescale, you can just choose which one is active. So if you put this to fluid timescale, only the fluid solver and the fluid physics will be run, and the solid physics will be frozen. So if I run this one step, you can see fluid physics added to steady state timescale, and then only the fluid physics will be run. As you can see, the von Mises are still 0. Now if I change this to solid timescale and then do this one step, you can see the von Mises are updated, and then the lift is pretty much the same. So this is a very easy way to switch between both physics. Now another advantage of this is that you can make custom stopping criteria for each timescale. So the solid timescale will only have to be run for one iteration. So you can make a new criterion fixed steps. I'm going to put this to 2. And then for the fluid timescale, make a new criterion, fixed steps 400, and then also a monitor criterion which monitors the lift, which is enabled, an asymptotic one, 1 Newton over 20 iterations. So now when we switch between those two, different stopping criteria will be set up, which makes it very easy to switch between both physics. So one problem that I came across quite often when experimenting with this the simulation is, so this is the displacement scene, and as you can see, the vector warp is it's not correct, it's just flat, and this means there's something wrong with your constraints. So in this case, as you can see, the contacts isn't correctly defined. So I could probably fix this by updating the contact mode interfaces. So now, as you can see, the context is fixed. And then check if these are still correct. So now, there are more phases added. I don't really know why, but for this one, I just select everything that has wing root in it. Now if we do this again for one step, the displacement should be fixed, as you can see. So now we have a nice displacement scene where we can see how the wing deforms. So now we're going to have to change some things in the simulation to make it ready for the HEEDS study. So first of all, we're going to have to fix this because as you can see, the replace part command does not show up for the assembly. However, it does show up for the parts itself. So you could technically replace the parts individually from within HEEDS, but that causes the surface meshes of both bodies to mismatch. So the vertices at the interface will not match, and that will cause problems for the solvers. So we're going to have to find a way to import these things, this assembly as a whole from within HEEDS. And we're going to do this by defining a macro. So I'm going to delete this, this assembly. I'm going to start a recording. I already made this one, so I'm just going to overwrite that. So then we want to import our step file. So we're going to tag these with the tags that we created earlier. So this is going to be the wing model. That will be recognized by the mesh. Now, a very weird thing about this is that you have to mesh this first before tagging the faces, because if you don't do that, the tagging on the faces will not work for some reason. So just make sure you execute the solid mesh within the body. Okay, so you have to tag the bodies as well, so that way they are actually assigned to a region. So as you can see, the region recognizes these. So now you can execute the solid mesh. So once the solid mesh is finished, you can tag the wing surfaces. And then the last step you have to do is to update the contact mode interfaces. You do this by update interfaces and then contact mode. So now the interfaces should be correct. Now you can just stop the recording. Now we're going to have to change some things in the region. So as you can see, this one already recognizes those two bodies because of the tags. The boundaries are also correctly set up. The only problem is the segments. So as you can see, these are empty, so we have to use filters to select those things automatically. So here I'm going to use the tags again, take the foil surface, do the same for the shear load. And then for these, I'm just going to find my name, fixed plane. And this one I'm going to do the same, but then use root as the name. Okay, so now those things should automatically select the right faces. Now, the second thing we have to do is to find a way to first solve the fluid physics and then solve the solid physics. We do not want those to run at the same time because that will increase the simulation length. So the way we do this is by making a new simulation operation. Add some operations so you can clear the solution, then mesh everything, then solve continua. And this is also where the time scales come in. So dissolve continua, you can actually no, this is the wrong one actually. You take the one's solved time scale. So we're just going to use the fluid time scale first, then make a operation that maps the data. Select the right data mapper, and then we're going to solve the solid time scale. Now we're going to create a macro that actually runs this simulation operation, because HEEDS does not have a standard function to run simulation operations. Run simulation. And then we're going to activate this and then run it. Now to stop the recording, you just wait for the simulation operation to finish. And then you can just press the stop recording button. Now to finish the preparation for the heat simulation, we have to delete this model again, because otherwise we're going to have two of those models, and that's not something we would like, of course. So now we can actually start making our heats, our heat setup. So we're going to use two CAD processes in parallel, and then one STAR CCM plus process. So we need two Siemens NX process, because we have two models. We have the basis model and then the modified model with the extrusion. So this is going to be the basis one. This is going to be the extrude one. We're going to make sure it exports it as a step file. So this one is correct. Now we're going to add the input files. We need the Java macros, and then we only need the basis step file, because the extrude step file will be imported using the Java macro. Now there's also one thing we have to adjust, and that is within the Java macro. So this is the region setup, which will import the assembly file. We actually have to change this path. So as you can see, this is the absolute file path. Now the thing is, when HEEDS starts a project, it will create another folder to store all the data. So which means that this absolute path will always point to the same step file. Now we need this path to point to the modified step file that is modified by HEEDS. Now HEEDS will always create a copy, another step file which contains the modified one, within the same folder as our zip file. So we can just delete this first part. So now this Java macro will search within the current folder, and then it will find the modified step file. So we just save this, and that should fix our problems. So the basis will be connected from NX CAD1. Oh yeah, you actually have to add the extrude path, the extrude step file, to the STAR CCM plus, otherwise it will not create that copy. So this one is going to be the basis step file. Then we're going to use 3 macros. So first we're going to set up, going to split the edges, then the region setup, and then we're going to run the simulation. We're going to do this before meshing. the clear solution will already be done within the simulation operations, so you don't actually have to select this. We don't have to mesh because that's also done by the simulation operations, and we don't have to run. So you actually don't have to select anything here because everything will be done by the simulation operations. Alright, so that's pretty much that. So now we can go on to the parameters. We're going to have two parameters. We're going to have height. Let's say just height. And then two responses. We're going to have max stress. And let's say the lift. Now again, we have to tag those. So we're going to have to change the height of the Siemens NX CAD files. So we go to expressions, then vertical length, tag. Now we have to do the same thing for the other Siemens NX file. So now it will change both models. Alright, so now we have to tag the output reports. So the max stress, this one, and then the lift, that one. Now the max stress, the height, I'm going to use a discrete variable because I'm not going to perform a optimization study. I'm just going to do an evaluation of different heights. So I'm going to create a set, which I'll call heights, and then add a couple items. So let's say 80, 110, 140. So we can select the set we just created, the baseline, which will be the first, which will be used for the first simulation. And that's pretty much the variables done. So we can now set up the simulation itself, the study. So we're going to do a evaluation, create a design set, and then a sweep. So a sweep, it will just use all the values defined within the set, and it will simulate all of those. So that is that, pretty much. So that wraps up the HEEDS setup. So if everything went correctly, we should be able to run our thing. Yes, of course, we have to save our HEEDS analysis first. Winglet height. So now it should run. Okay, so this is the final result. We can see that the lift converges nicely. And if we check the mesh, we can also see that the winglet height is actually changes. So that was it. I hope this video was helpful.